I'd like to lead off my examples with a real classic simple problem that you may have seen in calculus, probably did. Anyway, I'm going to approach it through the context of differential equations. So it's a natural growth and decay problem. The rate at which a population grows varies directly to the amount present. Alright, so this is in a type of language of variation that you may have seen in an algebra course along the way. I hope you did. Anyway, I want you to think about how this makes sense. For example, suppose that town A has 6,000 people in it and town B has twice as many, 12,000. Now if they're both growing at 1% a year, that means town A in 1 year will gain 60 people. And town B will gain 1%, which is 120 people. So you can see that the amount in town B is growing at twice the rate as town A. And it has twice as many people, so that's why I say the rate varies directly to the amount that's present. Right, so that's kind of a simple example explaining this relationship. And this is an assumption in any simple model to project population growth. All right, well, how does this translate to a differential equation? When you see the word rate, you think derivative. So the rate is a derivative, and it varies directly. That's an important phrase, to the amount present. All right, so let's say that the amount present is P of t. So this is the population at time t. And that's a lowercase t. All right, so whenever we have time, we'll use t for time normally. Population at time t. Now the rate is the derivative. So it's the rate of change of population with respect to time is the rate, or the derivative. It varies directly. It equals to a constant times the first power of amount present, Kp. So dp over dt, the rate at which the population is growing with respect to time, is equal to a constant times the population that's present. So there's a differential equation. If we wanted, we could have written it as P prime equals to Kp. Simple linear differential equation, first order. Okay, well, how do you solve this? Well, the first technique you learn in differential equations is the separation of variables. And so I have two variables here. I have P for population and T for time. K is not a variable. It's a number we'll solve for in specific instances. But if I multiply by dt and divide by p, in other words, do a little bit of algebra here, I've got dp over p is equal to k dt. So a little algebra manipulation, swap these around by the rules of algebra. The derivative dp over p is equal to k dt. Now we have separated the variables here. I've got p's on one side, I've got t's on the other side, and I have a differential on both sides. When I have a differential throughout the equation, then we can integrate. We can eliminate the differentials by integration. So we integrate both sides. And what is this derivative? The integral of dp over p is a logarithm. And it's a natural logarithm. So this is a natural logarithm of p, absolute value of p, is equal to k t plus an additive constant. So I integrate here. I have a constant times dt. Integrate, I get k times t plus c, the additive constant from this indefinite interval. All right, so a couple of notes here. In your textbook, Tenenbaum, they don't use the ln notation for natural log. They use log. In modern usage, log means base 10 logarithm, not natural logarithm. I will use ln your book will use log. I usually put the absolute value in because technically it's correct to have the absolute value there. Whoop, excuse me. So natural log of p is equal to kt plus c. But we're not done because I want to solve for the function. I want to figure out what function is this. So to eliminate the natural logarithm, you make it an exponent of its base. And the base is e. Remember, e is approximately 2.7182818. You have an e to the x button on your calculator. So I'm pretty confident you've seen e before somewhere. E to the natural log of p will cancel the e in the natural log. It actually cancels the absolute value too. So this literally just gives me the function p is equal to e to the kt plus c. Now I'm going to use another bit of stuff here, a little bit of algebra. I can break up this exponential function as e to the kt times e to the c. So think about the rules of exponents. When you multiply two numbers of the same base, you add their exponents. So I can work backwards from that and break this up. And now we're going to get to do something that's kind of fun in this course, I think. C represents a constant. Well, then what is constant e raised to a constant? Still a constant, isn't it? So sometimes we could play kind of fast and loose with these constants. I'm going to rename e to a constant as simply a constant. I'll just call it c. So I'm renaming c, and I have p of t is equal to c e to the kt. So this is the natural growth function and decay function, it turns out. Now, when time is 0, p at 0, in other words, at the beginning of a period we're monitoring for our population growth, we call the beginning time 0, then p of 0 would be c e to the k times 0, c e to the 0 power. And what's e to the 0? It's 1, so it's c times 1 is c. So we normally in this problem we're going to call p of 0 p subscript 0. P subscript 0. So now I can rewrite my solution just a little bit differently and say, okay, the solution to this differential equation is p of t, population at time t, is equal to the initial population, p0, times e to the kt. Alright, so there's the solution. Now, when you learn this in calculus, maybe even in college algebra, in college algebra they couldn't have solved this. They would just given you this. Calculus, you can solve this. P0 is the initial population, and K is considered the growth or decay rate. And so the population is growing, K is going to be positive. If it's shrinking, K is going to be negative. It's going to be a decay rate. So anyway, this is a exponential function, and you know, graphically it would tend to go like this. As time increases, it just keeps growing and growing and growing out of bounds. So now we can solve other problems with this. For example, let me throw some numbers in just for the fun of it here. I'm looking around for my calculator. I may have to pause my taping in order to find my calculator. In fact, let me do that. Hold on.